Awesome. So now we are going to the release section. So we're happy with the build. We pick one of these scenarios for our build pipeline. Now we want to see how we basically should be able to deploy it. So there are a couple of like differentiation factors here. There was a typo, sorry. Differentiator, I think this is correct, right? Yeah. So the first one is whether we're gonna basically have the model accessed interactively or in batch. We'll later on discuss it. Where we wanna deploy it, we wanna deploy it within the cloud, on-prem or edge. Again, the environment is very important, will limit us a lot. What ML framework was used, that's also another important factor. Whether we're gonna use a scaling in the inference or not is also important. Not every ML scenario can be inferred on a single node. You sometimes require a distributed computing to basically have the inference. And some other requirements, the security, the latency, etc. All of these also are differentiator factors basically to find what scenario to pick. I'll focus on two of them to elaborate a little bit further. So the online inference and the batch inference are like very important. The online inference, basically you want the result to be available immediately. So regardless of the environment, if it is on cloud, on phone, or on-prem, wherever you want to basically save it, you want the result to be available immediately. You cannot wait for that. Basically, you have to meet some timing requirements, or real time, basically, as it's called. So you need to basically have one environment up and running all the time to make it available for that model to be inferred. For this example, this is the type of environment we picked for this example that we're developing. But there's also another type of inference environment which is batched, which is mostly like scheduled jobs which you run to infer the model. We don't definitely have any timing requirement, at least it's a loose timing requirement. You can run the job overnight or some type of like weekly or monthly, and then get the result back instead of waiting for that result to be available. So you can use some on-demand or basically low priority or low cost environments to run that. Yes, please.
What might be QA in this context?
Yeah,
like within the ML team, or like general QA that might test the model's score, integration with the product?
Yeah, so the QA is very related to the actual problem you want to basically solve. For instance, if you're building an image classifier, you want to find it doesn't have any embarrassing results. So you want to run some sensitive tests at the QA stage before you want to promote that to the later, or you want to test bias tests and some other method which is very critical to the business, like will produce some embarrassing results. At the same time, you want to just make sure the model basically is not breaking, doesn't throw any exception error in the deployment environment, and etc. So it can be some tests on the system, actual system, and also on some dedicated machine learning tests happens at the QA. And if those are passed, then you want to promote it to the prod. If it fails, you basically want your pipeline to be broken there and do not move forward. Okay. Yeah. And the question was, what happens in the QA, and why we have QA here? If that makes sense. Awesome. So now we go to the second step, which is the environment. So we have like three main types of environments where you can provide your model and make it accessible. First is through a network link or network environment to host it somewhere, which becomes available through a network connection. You can basically access that. I'm sorry. The other place is the edge. And the last step is database. So for the network, that's basically the mostly, popular way to basically host your model on network environment is basically hosted through a web application or web API. It will be hosted somewhere, and based on a link, you can basically access that API and send requests and get anything you want, basically get inferred. Like hosting your model in Kubernetes is basically a little bit more advanced way of doing that. Instead of having a single serverless web application hoster, we can have a Kubernetes cluster to basically host your model, which will help you a lot. We'll discuss it a little later, which is the focus of our example. We use also Kubernetes for this example. The other way of hosting a model is through database. Sometimes you want to bring your model very close to data. Imagine you have like billions of data points. You, of course, you're not able to transfer your data all the time to the networking through network. Instead, you want the model to be close to your data. So most of the modern databases have the ability to host your model within the database. And what they usually do behind the scene, they basically virtualize the resources they have, like a singleton, basically methodology. They basically build a single model within that virtualized environment, and basically they pass the data in parallel to that model, get them scored, and save it somewhere in a new field, for instance, instead of moving all of those terabytes of data or billions of records over internet. And again, most of the modern database engines provide that. One of the coolest one is Database. Basically, you can train your Spark through a Spark mlib and then host it within the database, and that will be inferred in a distributed way again. Because the data is distributed in a Spark, inference also happens in a distributed way and is super, super fast. And regardless of, again, batch or online, that can happen batch. Like you can introduce it to a database, which is getting the stream of data. As soon as the data gets available, the data gets inferred. So it's really nothing to do with the batch or online way of, or interactive way of inference. And the last one is basically the edge. And the edge is wherever your compute resources is limited. Like for instance, the TensorFlow Lite Edge, you can basically host your model on a phone or Android phone, for instance, or reducing the precision of your a neural net from 32-bit to 16 or 8, which some of the frameworks will help you do that. Or using some runtime engines will basically help you to serialize the model in a much faster way, or in a much more compact way, which you can basically run better on a low power compute engine. So the other factor is the ML framework. So within the ML framework, it is very important that you basically pick the ML framework which you want to use when you want it to deploy. Like I've seen so many teams which, for instance, train on scikit-learn, then they want to scale it on Spark. It doesn't happen this way. You have to retrain again on a Spark mlib. That's very important that where you train it, and basically make sure that is relevant to the deployment environment. If that's not, you have to change it from the training time. And of course, different compute engine like GPU or CPU and other stuff are a main differentiating factor, especially on the deep neural nets. When we're trained, that will have significant impact on the performance and the inference and also the training time. There's also interesting called Open Neural Net Exchange, ONNX, which is a open source project we just started about 2 years ago by Microsoft, Facebook, and AWS. And the concept is basically to get any machine learning model converted into a runtime which is optimized for a particular hardware. Or you can get a PyTorch model converted into TensorFlow model. So these two interesting conversions were impossible before. So again, many of the teams have problems in moving away from TensorFlow because their models are trained in TensorFlow. But with this, they basically can convert it into PyTorch if they want to basically use a PyTorch model instead of a TensorFlow model. Many are also using ONNX for the runtime. In average, we have also used it extensively with Microsoft. At least we get, in average, about 2x performance improve when we convert into a ONNX runtime. But sometimes about 50, 60 times improvements on the performance time also was possible to get. So yeah, so it gets the model from any framework, converts it into the ONNX runtime, and then the ONNX runtime has very optimized runtimes for dedicated or different types of runtimes. It will be executed. That's a type of compiler world that you will compile it into that language, and then the JVM, for instance, and then JVM is optimized for different hardware instead of you think about optimization at the development time. And all of the packages have native converters to ONNX except TensorFlow, because that's a little bit political for Google. They don't want this to happen because they will boost and like expedite the people leaving TensorFlow community to PyTorch. So yeah, and some funny facts.
What's the thing on the upper right that's not?
Upper right? Yeah, so it's not a native. So all of them have like Keras. So like Keras and TensorFlow require a different package, but like for Torch, you have an export from from Torch package. You can basically export it to ONNX. But from TensorFlow and Keras, you have to basically import a different basically package to make that conversion. And some funny facts about it, like people are like arguing that for 2 years on GitHub, like is now the second most wanted feature on TensorFlow and is completely ignored. And yeah, so maybe they add it later on. I don't know. Yeah.
So what type of a database? What type can a model take? Oh, what type of model could be used along a database? For example, model exported from TensorFlow or PyTorch.
It's very different. Databases still have some limitations in terms of what models can be deployed. For instance, in Spark, it works very well with MLib model, which is any model which is produced by MLib. I'm not sure if you can deploy TensorFlow and scikit-learn within Databricks data frames, but you can deploy the TensorFlow model in BigQuery, for instance, natively. But I'm not sure if you can deploy scikit-learn into BigQuery. Yeah. So there are different, still have limitations, and the reason is the databases are built for very high performance or super high performance machines. And if they're not built to work well with that particular model, it will impact their performance significantly. So they don't want to basically risk that. So not any framework is definitely supported. You have to check where is your deployment environment and what are supported there. Makes sense. All right, so now go back to our scenario. We wanted to, it will be trained and deployed on cloud. It will be interactive online through the API. It will be trained and served natively through TensorFlow. No ONNX I used, but of course you can go ahead and use ONNX. Is cool. And the model and the API are Dockerized with an image and then shipped to Kubernetes as a container orchestration engine. But now let's discuss why we need a container orchestration or why Kubernetes is important. So going back to our example, let's say we have images, and basically we have assigned each of them to particular capacity, or they basically consume part of our machine, not everything. And if you want to scale, vertically, we can be able to basically do that. We can copy that across the machine until we consume all of the resources that are in one machine. But what happens if you want to basically scale it horizontally? Like if you want to basically have multiple machines running these containers instead of like running different basically VMs or like instances on AWS and run Dockers on them and you manage everything yourself, you want something to basically be able to help you do that. Or what happens if you want to basically maintain the communication? You have to add a load balancer yourself, manage all of the incoming requests, and manage all of the load balancing and communication problems and complexities. Or what happens if something fails? You want to go through disaster recovery yourself. You have to make sure all of the VMs are running properly, all of the containers are running properly, and all of these complexities. So all of them are handled by a container orchestration engine, which Kubernetes is the most prominent one. We have some others, but Kubernetes is the most prominent one. So it does all of those tasks. It's basically an open source environment which can help you to orchestrate any kind of containers, in particular Docker containers. Again, we do have other types of containers. We have Linux containers, for instance, and other stuff, but the Dockers, again, are the most dominant type of containers. And the architecture, the way it works is that we have a master and we have nodes. And within the nodes, you can basically deploy as many Dockers as the resource allows you to do that. And it basically manages all of the management of the nodes and the scale. So it requires like another course to go through the Docker. Kubernetes is a very complicated beast. But going back to the design patterns for deployment, you would basically use Kubernetes for deployment. But there are multiple ways to basically orchestrate Kubernetes. So you can have one of these clusters, like this is again a cluster. We have one master and have multiple workers. You can have the same thing again. You can have multiple clusters on a cloud or thousands of clusters for different purposes. But you can consume them in different ways to basically deploy your model. One way is to completely isolate the environments from physical environments, where you have one Kubernetes cluster for dev, one Kubernetes cluster for test, even team-based, one Kubernetes for team 1, one Kubernetes for team 2, and then completely isolate them. The other way is to basically have one Kubernetes environment and then you logically separate them. So you would basically divide part of the node 1 to some type of job or teams and etc. and then basically you can divide that. This is the job of the operations team. You don't have to get deep into this at all. This is not part of the ML practitioners. If you're ML engineer, yes, but if you're ML scientist or data scientist, you should have a good like high level understanding, but do not need to get deep into this. They don't give you 2 salaries, so I'm just kidding. But it's cool to know how it works. So going back to our environment, we basically had in our release pipelines, if you remember from the picture that we had here, in the release pipeline, we had a QA and then we had a prod, right? So we have a QA and we had a prod environment within a release pipeline. The way I wanted to basically design it in deployment, we want to have one Kubernetes cluster where I deploy a prod web service and also prod web service into the same Kubernetes environment, into 2 different basically containers and pods. And again, from pod perspective, pod is the smallest execution unit within Kubernetes. Within the pod, we can run couple of containers, and within each node, we can have couple of pods. Is a nice way to basically separate the types of jobs there. Yes, please.
But if you're going to do this logical division, is there a way to like ensure like data securities, for example, like production data versus like dev data and staging data?
So whatever is running there is the inference environment, right? So it won't be used for training, it will be used for inference. So whatever you pass to that will be inferred. So it depends on the consumer rather than the actual model. But also in terms of all of these checks we have to do at the application level. Kubernetes, what it helps you to basically seamlessly deploy an image into an environment, which is very complicated, but it's abstract so many of the complexities there. But in terms of the application layer, security and governance needs to be handled at the application level. My laptop is done. Have to change the oh. All right, so if you could help me connect this. So we're gonna finish it by 9 and then we're gonna start the second section.
Don't you wish you had this kind of service all the time?
Pardon me?
Don't you wish you had this kind of service all the time?
Thank you. You're lovely.
Where's the other batteries?
Thanks. We've been back live. Awesome. So now again, going back to that, our MNIST release pipeline, we want to, after these artifacts are introduced, based on the model, we want to adding a new model. We want to kick off a new pipeline, which what it does, it first containerizes the model, creates a Kubernetes cluster if this is not already created, and then deploys the containerized model into the Q&A, and then it will, if it is successful, it will deploy it within the prod. That's basically the whole approach. And from the prod, it will basically talks to some sort of monitoring service, in this case, App Insights, where everything happens there will be kept there, and then you can subscribe it to an event later on for later retraining and other stuff. Yes, please.
So like, there's probably, I'm guessing, 2 QA elements. So like, yeah, my understanding of the QA came in at this web service level, but then at that point, because you've already done model testing in the ML pipeline, this QA is specifically just testing like the API essentially. It's not really testing, it's not creating, that QA person is probably not creating some sort of report of like the quality of a model at that point.
So the QA, so whenever you're building that release, similar to the build pipeline, there's a set of steps.
Yeah.
Which you can basically run. The first step is in command line, which runs Python, which inside it creates a Kubernetes, for instance. A couple of steps you can do. So based on the type of machine learning problem, the data scientist can introduce another test.py only for QA. And basically that operations team can introduce another command line which kicks off that test.py file to check something within the model, and that can be another step. And if those tests are not passed properly, it will fail. And you're right, some of the tests happens at the training time during the pipeline generation. Some of them can happen here, which are can be very focused on the operational system, but how the model actually works in the actual wild, or some final very important tests, which are beyond sensitivity and other stuff, bias and other stuff that you would test here instead of the training pipeline. Again, one of the reasons you may need to have different types of tests is that you're deploying this into Kubernetes, which is the engine is different from the training time. Training time you would deploy on a VM or a set of VMs, right? But this is a different types of orchestration engine to run your Docker image. So again, you may have different types of problems facing here instead of there. Like latency should be different because you have different types of Java scheduler here, different types of Java scheduler there. You want to make sure your assumptions are valid in both two stages.
Question?
Yes?
If there are Kubernetes cluster across the teams, can you go back to your slides with the Kubernetes cluster, I suppose? Okay, if there are Kubernetes clusters across the team, might they share one master cube, or each team on that diagram has one?
So, so again, it can be two different ways, right? So you can basically divide it into divided resources based on, again, the type of job or the type of resource they require. But the more separation is always better because it will make it easier for you to manage, and also scheduling and all of some of the complexities that can happen based on the lack of the resources can also go away. But again, it really depends on the type of the job. But in this example, because it's very simple, and of course there's no other team going to access that, also it's not used very significantly. You just use one Kubernetes environment. It's very lightweight and also will be deployed there, but it's definitely not the case in fully production environments.
Okay, yeah.
And definitely the operations team who are expert in Kubernetes need to manage this, and not the data science team. The data science need to know only they are running this on Dockers, and these are the requirements, and they know how things run on Kubernetes. But if there's only data scientists or there's no operations team, this is very risky a little bit because it's not a shoot and forget. You have to be able to maintain that environment if it fails and other, because it has abstracted so many of the layers of complexity, but it still is a very complicated environment. Some is over-engineered in my perspective, but still it's a very powerful environment. Awesome. So let's discuss what happens within the release pipeline. So within the release pipeline, when a new model gets registered in the model store, you want to kick off an event. You want to trigger something, right? So that trigger basically what it does, it goes to the second step. It fetches the model from the model store, which is the latest model. It will package it into a container. Why? Because we want to make sure this model runs anywhere that basically is able to run this image, right? So it will package it into a container, you provide a dependency, you provide all of the things which is required to run this Docker anywhere you want. And in addition to this image, in addition to the model itself, you have to provide an inference file, which to your point, that is the time you basically introduce the inference file. And what does this inference file do? It basically, very simple, in a simple way, you can go very complicated too, but it has to have two steps. One, loads the image, loads the model, and the second step gets the input data and infer it based on the loaded model. Basically, these two has to be there, but you can always increase the steps to more complicated steps. All right, then the next step is basically create a Kubernetes cluster if it is not already created. Create image, which basically contains the model and those score. Basically, that image will be introduced and deployed as a web service in the Kubernetes cluster. What it does basically, it provides a nice API to be able to access that application, which the application is your inference code, which infers based on your model. So again, you have one application, which within the application, it loads the model and infers. That is containerized and packaged, right? And that package is introduced and provided through a web API on the Kubernetes machine, basically what it does. And it can always like provide scalability. That is like a single container, but you can always like increase that and elastically based on the loads. So if you hit more loads, you can be able to increase it and basically create more containers from that image or reduce it down to one if you want. And and then we have two steps, one QA and one prod. So for QA, you go through this, and for prod, you have to again deploy it into another web service, which is for prod environments. So that's what you do. And this is how it looks like at the end, which this is the release image. So this is basically the artifacts which are passed, and the artifact, one of the artifacts is the build artifact, which is the code, and the other artifact is the model, which is connected to your workspace. So once the build registers a new model, but this time was the version number 6, it will basically trigger only on the model. So based on this, it will basically kick off the staging, Q&A and prod. And going to the application monitoring, I'm gonna go a little bit faster. So whenever you create that web service, you want to register that web service, you can basically introduce and mention that you want to collect the model data and you want to basically enable app insights. If you turn these two to true, wherever you write print within that score.py file, that will be saved within the application insights. Going back to that initial default resources which are created, the storage was created by default when you create the ML workspace. There was another thing which we discussed today, which is the model registry. There is another service which is created by default when you create it in the behind, which is called application insights. That's basically NoSQL database, which you can store any type of log files into there. So that will be basically saved. So if you go to the portal, you will be able to see the application insights here, the link, and then you can go there and then basically see what type of logs is basically saved. So for instance, for this one, which is like model initialization, it's hard to see, but basically it will add a field here, which tells you exactly what time it was based on this. So you can record anything you want and then make it searchable. And you can basically subscribe an alert to this, and based on that you can subscribe a like Lambda style function and then kick off like retraining afterwards. So going to the retraining, the retraining happens based on some logs. So so you can, as I described, you can subscribe to that application log to kick off a new new job. You can basically define that function to do something, and that something can be retraining. And retraining can happen based on so many different things, like model decay can be tested, so you can have some labeled data pass it to the model based on some function. If it is is reducing based on the time over time, you can basically hit the retrain. Or if there's a model data drift, and the data drift is basically it's more related to the columnar data. And what it does is basically it tells you whether the distribution of data based on the features are changing. Like for instance, you can like use some chi-square test to test two different distributions and come up with a threshold, and based on that threshold, you can basically kick it off. In the deployment, there's also there is also data drift. You can basically use that if you have columnar data deployed. In our case, it's image data, so it doesn't work. But if it's a columnar data, you can basically enable the data drift. And basically, you can get the data drift metric over time as it goes, and introduce your training data. And based on that, it understands how your data is changing over time. And based on a particular threshold, it will basically kick off a pipeline, which can be your retraining pipeline. But the successful retraining pipeline, going back to the initial discussion we had, mostly when it happens, when there's a significant change in something. So one of them can be a data set. So you can have some statistical check test to basically make sure that the data is changing over time, and based on a threshold, you trigger some sort of retraining. It can be one simple reason that you receive a massive data, which may change your model. So you want to sometimes train it based on a very simple factor or complicated factors. But it's important that you think about retraining from dynamic fine-tuning. If you do not do dynamic fine-tuning in the retraining pipeline, basically you won't be able to get anything. Unless for only one case you may get something better, and that's the case, that's the time when you're getting a lot of new training data. But if that's not the case, if you do not do fine-tuning in the retraining pipeline, you basically will not be able to get anything further. And you can leverage the hyperdrive step or AutoML step within the training pipeline to always fine-tune for a better model, instead of having a static set of hyperparameters and you always try that. And especially if you have like thousands of models, again, we're getting to that stage that if you want to like predict the energy for like a store or like a retail store, which they have like 2,000 stores for instance in Canada or somewhere, you cannot train a single model and push it and use it for everywhere. You have to train dedicated models per store or even per room, and that makes it very complicated to train and fine-tune it as a single person. You have to use some automated metric or automated technologies to basically do that. You may not get the best optimal performance with AutoML, but you'll still get something valuable, which is better than every one of those stores of those rooms within those 2,000 stores get fine-tuned by a single person. That's not scalable, definitely. And yeah, so now we can have a 10 minutes rest and break, and then we can kick off the lab section later.